Okay, so this is from this text here, this book, Build a Large Language Model from Scratch by Sebastian Rascha. And here's the table of contents, and we're going to skip chapter 1. We'll go directly to chapter 2. So chapter 1 is kind of an overview, but it might be a little bit kind of confusing if you don't already know what he's talking about. So let's just start with chapter 2. So the task here is going to be coding an LLM from scratch, and he's going to break it up into these 3 different steps or stages. So here he says implements the data sampling and understanding the basic mechanism. Now we'll see what he means by data sampling because not exactly clear what that means right now. And here he breaks this up into 3 steps. So data preparation and sampling. Then we talk about the attention mechanism, which is critical to an LLM. And I guess he discusses the overall architecture. And then after we build that, then we're going to engage in pre-training, which means, well, in terms of like a large language model like ChatGPT, that would mean like training it on the entire internet. But of course, we're not going to do that by ourselves in this book. So he's just going to use some sample data set to pre-train with, just to give us a feeling for what's involved. And down here he says this chapter focuses on step 1 of stage 1. So I guess we're just going to start with this in chapter 2, which is where we are right now, chapter 2. So here he says you'll learn how to prepare input text for training the LLM. So we're going to have some text, but we have to convert it to actually numbers, to embeddings, and so on. So we have to do some pre-processing of the data, I guess we can call it that. And he says we're going to split, and in fact we have to take the text and split it into individual words. So we have some long text. I think in this chapter he's going to use something for some short story. So we have this relatively long piece of text, and we want to convert it to words instead of just one long string. And he's going to convert it to individual words. Sometimes we'll do slightly different way of breaking it up, maybe not exactly words. It could be actually subwords. That's a technique that was used for ChatGPT 3, I think, 3.0 and 2.0 and so on. But for simplicity, I think we'll just use individual words to separate the text into individual words, which can then be encoded into a vector representation. So each word can then be turned into a vector, and as we call it, an embedding, but it's just a vector. And we'll see what that means in a minute. And he does mention this other type of tokenization. Instead of splitting up exactly into words, there's something called byte pair encoding, which was used for ChatGPT, as I just said. But for simplicity, you can just think of it as just splitting it up into words. And I think that's what he actually uses in building this LLM. So now we discuss what is meant by an embedding, a word embedding, and that's just taking a word and trying to represent it as a vector in a vector space. So, we could have a 2-dimensional vector space like this, and we could try and represent the word dog in this vector space, in this 2-dimensional space. We could say, okay, well, dog is here. And what we mean by here is, well, it means it has an x coordinate of this and a y coordinate of this, and so we could represent the word dog as whatever the x coordinate is here. Let's say this is 10, just make it up, and this is 5, just make it up. So this would be the embedding, according to this picture, if this picture were true, would be 10, 5. So we've represented the word dog with 10, 5. We might have another word like cat, and maybe that, of course, that's going to have a different set pair of coordinates or a different embedding. Now, of course, I just drew 2 dimensions here because it's hard to do anything else. I could try 3 dimensions, but that's pretty messy. And then when we go to any larger number of dimensions, that's basically impossible. But that doesn't mean we couldn't use that. Like we could say, okay, I'm going to represent the word dog by 2, comma 5, comma 3, comma 8, or whatever it is. That's a 4-dimensional representation of the word dog. Now, the real question is, why would we have 10 comma 5, or what's the um, importance of the coordinates? Are they just completely random or not? Well, they could be just completely random, but it would be kind of nice or kind of interesting if we could have them have not just be random. So what do I mean by not just be random? Well, like for example, we might think that dog and cat are more similar than dog and teacher versus dog and cat. We would think that maybe dog and cat are sort of more similar in their meaning. What I'm saying, they're sort of more similar in their meaning than dog and teacher, or dog and teaching, the verb, or dog and smelling, or dog and dreaming, right? Dog and dreaming are probably don't have uh, are not as close in meaning as say dog and cat. So if that's the case, then I would hope that dog and cat wouldn't just be randomly assigned, but rather dog and cat would have sort of similar coordinates, or in other words, the place where dog is and the place where cat is would be sort of close to each other, as opposed closer to each other than say dog and laughing. So maybe laughing is somewhere over here somewhere, and cat is maybe somewhere like over, whoops, sorry about that, but cat is somewhere like over here. So dog and cat are then closer together than dog and laughing. But but how do we do that? How do we um, have that happen? I mean, we're not going to sort of do that manually. But anyway, it would be nice to have that property as opposed to just randomly assigning dog and cat random coordinates. So we would like to see how in the world we could do this. And I remember when I first saw this, I was completely amazed that it actually worked. But it does work. So we'll see um, how this is done in a little while. But that's the idea of word embeddings. Hopefully, they they somehow represent the meaning of the words, in the sense that things that have similar meaning are close together. So he says this is called an embedding, but it's just a vector representation, or like a pair of coordinates, or 4 coordinates, or whatever we happen to do. Now, one last point, and that is we have to know how to calculate the distance between, if this is cat, I'll just write C here. This is cat, the distance from here to here, but we know how to calculate the distance of 2 points from each other. So that's not actually a problem. But we do have to have that concept of the distance between 2 points in order for us to talk about two vectors being closer together. We mean the points that are at their tips are closer together than, say, the point up here and dogs. Now he says you don't have to, you're not stuck just with, our data doesn't have to just be text for this to make sense. We could have, if we could represent an audio sample as a vector somehow, who knows how to do that, but if we could, then we could talk about two audio samples being close together or not close together. But we're not going to talk about that in this discussion, but you could do it. And the same thing for video. You could have, you could represent a video, maybe just a video sample, small part of a video, as some vector, And then you could have two different video samples, and they would be two different vectors. And again, we could then talk about whether they're close together or not. So here he's saying we can represent text here as a three-dimensional vector, here an audio sample as a three-dimensional vector, and here a video sample as a three-dimensional vector. So he's going like one step beyond what I drew here. But we don't even need to stick at three. We could go to 4 or 10 or 100 or 50 or whatever we want. But of course, the more you do, the larger the so-called vector, the larger, more elements in the vector, um, that's sort of using up more data, of course. If you're using four numbers to represent dog, that's more data than, or more space in the computer than two numbers to represent dog. But on the other hand, there's a kind of a trade-off. You're using more data, but you also sort of typically get more kind of precision when you do that. So it might, in other words, when in your LLM might perform better if you do that. So now he makes a little bit of a kind of a little hard to understand, a little bit abstract statement here. He says, at its core, an embedding is a mapping from discrete objects. What does he mean? He means text, words, for example, such as words or a particular image, or even well, let's say such as a word or an image to points in a continuous vector space. What does that mean, a continuous vector? It just means this. This means, like the plane or 3D or 4D or whatever. Why do they call it continuous? Because the numbers, this is like, we call this the x-axis and the y-axis, and typically we say, anything on the x-axis is okay. I can have 1.5, I can have 1.6, I can have 1.66667 or whatever, right? So that's when we have that situation, we call that continuous in mathematics. So it's kind of a complicated way of saying kind of not not necessarily not necessary to be that complicated, but anyway, he's being kind of mathematically correct. So we're taking discrete objects, that means text, words rather, but he says it can be images, and he says instead of just one word, we could have like sort of many documents, and each document could be represented by just a single vector. So that's very different than representing each word in the document by a single vector, but we could do it. We could shift our focus, so to speak, and take each document. Suppose we had 10,000 documents. We could represent each one of them by a vector, not each word in each one of them, but just the the documents, one document, one embedding. I did that a long time ago when I was working with Twitter data, and I represented each tweet as a single vector. So I'd have, I had like a million tweets, so I'd still have like a million different vectors, but I wasn't breaking the tweets necessarily up into words. And he says the reason for this, the primary reason for this, of using embeddings, is because we're taking non-numeric data, like a word, and converting it into a format and a vector, or a list of numbers, that neural networks can process. And now he mentions that sometimes when you're working with like a whole document, we do that often with, or maybe just paragraphs. When we talk about RAG, which is a kind of important technique these days in working with LLMs, that's retrieval augmented generation. That's basically when you take some documents that the LLM hasn't been trained on, and you want to sort of use those when you're querying the LLM. When you have a prompt, but you'd like it to refer to maybe your company's proprietary documentation, which hopefully the LLM hasn't been trained on that yet. In other words, like ChatGPT or OpenAI didn't have access to your company's proprietary documentation, hopefully. So, but you still want to use that. You want to use the LLM to work on that or work with that. So you use this. What you want to do is to kind of treat each paragraph, for example, in your um, document or documentation as a as an embedding, or assign it an embedding, and this way you might be able to work with it. But he says at the bottom here, we're going to focus on word embeddings, not paragraph embeddings or document embedding. So here he mentioned something called Word2Vec, which was very popular a couple of years ago, maybe 4 or 5 years ago, as an example of doing this kind of embedding. But probably in this text, I haven't gotten that far yet, but probably in this in his way of doing things, he's not going to use Word2Vec, but he's going to sort of create these embeddings as part of the whole LLM process. So, in other words, we could um, create our embeddings using some algorithm like this, or in fact, we could even just uh, get the results of someone else having assigned um, embeddings to each word. But they use Word2Vec to do that, and then we can just take those embeddings and hopefully, and we can use them sort of as a pre-cooked part of the process. And again, hopefully, the whole point of this is that if somebody uses Word2Vec and they create these embeddings, again, hopefully, dog and cat are kind of close to each other in that scheme. But we're not actually going to use that. We're not going to do it that way. We're not going to use pre-trained embeddings. We're going to create our own embeddings based on the our particular training data. So that might be better than using sort of somebody else's embeddings. Uh, our embeddings will be more relevant to to our training data. So it might be better. Okay, next he says word embeddings can have varying dimensions, and we said that already. You can have two. Actually, in fact, you can have just one. So I use 2 dimensions here, the 2 blue dimensions, but we could actually just use 1 dimension and just say like dog is 4 and cat is 3 or something like that. But so we could use just one, we could use two, we could use three, we could use four. He says we can use one, we can use 1,000, from 1 to thousands. And he says that a higher dimensionality might capture more nuanced relationships, but at the cost of computational efficiency. So here's another picture. So eagle, duck, and goose maybe are close to each other after if we can train these embeddings. We'd like that to be true. And squirrel might be a little bit further away from this group, and these words would be further away from that group, and so would these words. And here he says the advantage of optimizing the embeddings as part of the LLM as opposed to using Word2Vec instead of using Word2Vec is that the embeddings are optimized to the specific tasks and data at hand. So it could be beneficial to create our own embeddings as part of our training process. So we can talk about higher dimensional embeddings, in other words, like having an embedding size of 1,000 or whatever. And he said this. He says the smallest ChatGPT model. So this was back before ChatGPT. I'm sorry, GPT-2 had this embedding size. So there were 768 dimensions. And then ChatGPT-3 had this many dimensions. So that's a lot of dimensions. But as we said, that might give us more precision. Okay, so next we're going to talk about tokenizing the text. So that just means taking the text and breaking it up into individual words, which seems simple enough. But as we said, you don't have to do it that way. There are other techniques, and in fact, ChatGPT used other techniques. They didn't do exactly just words. Let me see if I can find a picture of that. Okay, let's see how this works. So, let's see how this works. So we'll try it. So this is the latest version, I guess. There's an older one. Let's see what the older one does. So let's try it. Okay, so here. So it breaks things up like this. So like don't is DON is one token, and then this is a separate token. And here, indivisible is split up into what, 1, 2, 3 tokens. So it's not just, it doesn't take a sentence and break it up into words, but it breaks it up into these other, what we call tokens. So this is called a tokenizer. This that we're playing with is called a tokenizer, and we can see how it's working. Let's see what happens if we try this one. What do I have to do? Okay, let's try this. Okay, so this is different, right? So before I think we had 3 tokens. Now this version of the tokenizer only breaks us up into 2. But still it breaks it up into 2. And this one I believe was broken up into 2, but now it's only 1 token. Okay, so that's an example of this tokenizer. So anyway, we want to talk about tokenizing, and he's going to do it in a very simple way, that kind of a natural first approach, and then he's going to create a class that does this. So somewhere down here. So simple tokenizer version 1. So what it's going to do is we're going to initialize it. So we have to initialize it with some our entire so-called vocabulary. Anyway, we'll talk about that in a second. But anyway, we'll just initialize it, and then we'll test it out. So once we've initialized it, here's some text, and we want to tokenize it. So we take our tokenizer, and we do tokenizer.encode, which is one of the methods he's written here. He also wrote tokenizer decode. So let's see what this does. So tokenizer encode, and he's assigning that to IDs. And if we print out IDs, we see we get these. So what this is doing is it's taking the text, it's splitting it up, and then it's assigning numbers to each of the words. Actually, the numbers come from, we feed it sort of the entire set of all possible words that we're considering, and we have we assign each of those words a number, an ID, and then here we have some of those words here. This is, our vocabulary might be 100 words, or it might be 1,000 words, or I think for ChatGPT it was 55,000 words. So that's the entire vocabulary that ChatGPT sort of works with or understands, and each word in that vocabulary has an ID. So we might have like boy, it has an ID of 0, and girl has an ID of 1, and so on. So anyway, each word has an ID, and then we take this and we want to know what the ID was for its, and for the, and for all the tokens in here. And let's say the tokens are just the words. So what's the ID for this word, and this word, and this word, and this word, and that's what we have here. So we have all the IDs, and that was, how did we get that? We initialized our tokenizer, and then we applied encode to our text. And then what we can do is we can take these numbers here, which is IDs. We can take these numbers, and we might want to go backwards and figure out what were the tokens associated with each of these, or in other words, what was the text associated with each of these, and that's what the decode function does. So the encode function um, goes from the words to the numbers, and the decode goes from the numbers back to the words. So let's see if that works. So we do decode IDs, and we print that, and hopefully we get this. So this is basically the sentence that we had originally. Okay, so this is the simple tokenizer version 1. And if we go back a little bit, we can see that we start with some text, and then we break it up. That's called tokenizing it. And then we take these tokens, and as we just saw, we're going to assign IDs to them. Now, there is this notion also of the vocabulary. So let's go back and find that. Well, let's just start here again. So tokenizing the text, and they say they're going to use this short story by Edith Wharton called The Verdict for training. And here they just have some code to download that and some code to open it. And then they also print some of it, the first 100 characters, and also the total number of characters in the short story. So there's this number of characters. And then if we print out the first 100 of them, we get this here. So we want to tokenize this basically a long string of text that has this many characters in it. But characters are not really what we're interested in. We just want to, but anyway, that's just giving an idea of the size of it. But basically, we just want to rip it into tokens or into separate words. So he's going to use the regular expressions library to do this. And this is not typically what you would do in reality, but this is just a good way to show us what's going on. So let's suppose you have this text there, and you split it on the white space. So that's the kind of the basic idea. And once you split it, you can get the result here and print that, and you get a list, and it's got like hello, and then I guess it has white space, and then it has world, and then it has white space, and so on. So it's a list with, but we don't really want, well, he says later actually, we might want the white space or we might not after we split it up. But at the end of this, I think you can see that the period is not separated out. So he doesn't like that. So he wants to do something to separate out the period. He does some irregular expression here. And now we get a separate element of our list, which is the period. And then this is, I guess, an empty space. And then he does some more stuff here, and he gets a slightly different version of it. Looks like this. You can go through this and see. So like I guess at this point we have this, and then we tokenize it like this. And now he said it, now he tries it on the first 30. Sorry, now he applies it to the whole story, and here he puts in the raw text in here, and then calls it preprocessed, and then he strips out something, and then he prints the length of it, and he gets the length is this. I guess that's how many words there are, or whatever we would call them, tokens. And if we just want to see a slice of those, we can see I had always thought Jack ... and there's a comma there, for example. So now we want to take the tokens and put them and convert them to IDs, but he says we have to build a vocabulary first. So what this means in this case is, since we're only using that one short story, we just want all the words in that short story, and we don't want them repeated. We just want each unique word, or maybe we have to call it token. So here's the vocabulary. Maybe the first word might be brown and dog and fox and all of these. Well, I don't think these are actually in that story, but that's the idea. So I guess what he does here is he takes all the words. I'm sorry, he takes the whole. He takes the text and he splits it, and that's called pre-processed. Then he does something else to it here. So we have basically the text there tokenized, and then he applies the set function to that, which probably finds the unique set of items in pre-processed, and that's called all words. So this might include, or probably does include, periods and question marks and other assorted sort of what we wouldn't necessarily call them words, but includes those as well. And now we can get the length of that, and that's the vocabulary size, and we can print that out. And then according to, I guess it turns out that there are this many. And so he has all words here, and he's going to enumerate that. So that's going to create a dictionary, and so it's going to be the token and the ID. So we're going to have a dictionary with like the first word might be, let's just make it up. Let's say it was dog, and then it might be 0. That would be the first one, or actually I think it would be the other way around. Sorry, it would be the other way around. The 0 would go here, and dog would go here. So we'd have this kind of dictionary, and then we can print it out and see what it looks like. No, I guess I was wrong. It's this way, and this way, and this way, and so on. So it's the integer, the ID, comes second in this dictionary. So now with this dictionary, we can find each word in our that we're trying to encode, and so we take a string, a sentence, some sentence, and we're going to try and convert it from the sentence to tokens, and then from the tokens to the IDs, so these things. And so here we have the brown dog, so I guess maybe the is 7 and brown is 0, and dog is 1. So we would take this some text, and we'd get something like this as the encoding of the text. And then, like we said, we could also write a decode. So this class takes vocabulary as an argument. So we have to feed it our vocabulary. And then, once we feed it our vocabulary, then we can feed in some text and put that into our tokenizer encode method, and we get out like what we said here. And then the decode of that is the original sentence or something close to it, like this. Okay, so we've completed that step, which is tokenizing and encoding and decoding based on the vocabulary. We need to have the vocabulary if we're going to use this class. Okay, so now he says let's try it out on some arbitrary sentence like this. Now this was not in the text. It was not in the short story. This is just some text. So hello, do you like tea? And we try it out. We encode text and we get an error. And the error is that this was not in the vocabulary. So when we're looking it up, we can't find the key hello. So it gives us a key error for hello. So a little hard to believe that this short story doesn't contain the word hello, but apparently it doesn't. So this may not be a problem just for this sample that we're just constructing here, but this might actually occur when we actually try to do training. So we might encounter something that isn't in our vocabulary. So we have to have a way to deal with that. So we'll talk about that next. So he's going to end up creating a new version of the tokenizer, version 2, a simple text tokenizer that handles unknown words. So when it encounters an unknown word, it's not going to give us an error, and instead it's just going to give us this symbol here, UNK, which means unknown. So whenever it comes up with whenever it encounters an unknown word, that is a word that's not in the vocabulary, and we try to encode it, instead of giving us an error, it's going to fill this in. So before we go back and see what he did, let's just test it out. So here, hello, do you like tea? And another piece of text we'll test it out on. Hello, I'm sorry, in the sunlit terraces of the palace. So now we're going to take text 1 and text 2 and join them. And then also, I guess we're going to join them and attach that to this token here. No, that's not what it does. I think it joins these two and puts this in the middle. So that's what join does. When you do this dot join, you get that's what happens. So what we're going to get is we're storing that here. So when we print it out, it's going to be hello, do you like tea? And then this special token, end of text, which is just supposed to say that there was like a sentence here and then it stopped. So and we want to say that's the end of like the first piece of text. So we just want to have that encoded into our representation of the short story. So every sentence, we're going to have end of text and then the next sentence if we use this method, if we use this class. Okay, so anyway, we have the text and it looks like this. But remember, hello is still not in our vocabulary. So last time when we tried Simple Tokenizer, I think we got an error. Okay, but when we tried to encode it, we got an error. So now we're going to try it again, but we're going to use our new version, version 2, and we're going to encode our text using our tokenizer. So this should give us a bunch of IDs, because that's what encoding is supposed to do for us, is to return the IDs. So we're going to take all of this and get a bunch of IDs, like this might be 7 and this might be 4 and so on. But remember, our vocabulary is pretty big. So these numbers could be much bigger than 7 and 4. And actually this piece here is added into our vocabulary. We didn't see that yet, but it is. It's added into our vocabulary, but it's added in at the very end. So this is going to be like the largest ID in the whole vocabulary. So if we try to encode this, as we said, we're going to get a bunch of IDs, but this thing is going to be large. I don't know about these, but this one will be large because this is the very end of the vocabulary. So we get all of this. This is pretty large, but I'm sorry, but hello is an unknown word, and that's also added into our vocabulary. The unknown token is added into our vocabulary, and that's also at the very end of the vocabulary. So this is going to be large, and because this is unknown, it's also going to be large. It's the unknown. It's going to be represented by the token unknown, the unknown token. Um, and actually, I think this one is at the very end, and this one is the second to last in the vocabulary. So this will be one unit larger than this in terms of ID. So it is. You can see this is 131. I'm sorry, 1131, and this is 1130. So these are the last two IDs in the vocabulary. So remember, our vocabulary was, I guess it was 1129. Was that right? So it says 1130. That's the size. But remember, our tokens began at 0. So that's why this is that number. This is why 1130 is actually the second to largest token, and the which was I think end of text, and unknown was the largest one, which is 1131. So that's what we get. Unknown is, I hope I said that right, 1131, and this is the end of text, which is 1130. And then we can decode what we just encoded, so we can take all of this and decode it, and if we do that, we get unknown, do you like tea, end of text, in the sunlit terraces of the unknown. So I guess that was another word, which was unknown. Now, the period is the very last piece of this output. So the period is 7, sorry about that, but this one is the same as this one, and those are both encoded as the unknown token. So we get unknown and unknown for each of those. So this is many different tokens can be all named unknown, or they're all unknown can point to many different tokens or represent many different not tokens but many different words, or maybe it's many different tokens. Either way. So the unknowns were hello and palace. So both of those are called this here. And both of them have this ID. Okay, so briefly, we take our pre-processed and we we sort it, we create a list out of it, and we first do the set function on it to get the unique elements. And then we we extend it with this and this. And now we have a new vocabulary, which has these two elements on it, and we can use them. And now we see that the length is this, where I guess before it was this. And if we want to look at the last 5 of them here, we can print them out, and we see that we have younger, yourself, and then this one, and that one. And then in our encoding, we're going to add in an if statement here. And if we don't find the item in our vocabulary is called this. So if we don't find it in our vocabulary, if the item's in there, we're going to convert it to its item number, but otherwise we're going to convert it to this. So that's how the unknown token is used. And then, as we said, if we have two sentences, we'll we can indicate the end of the first one with this end of text here. So we get when we encode it, we get this, and when we decode that, we get this. Okay, next he mentions that depending on the LLM, some researchers also consider additional special tokens. They've got a beginning of sentence token, which they might use something like that. End of sequence token, which is basically this one here, but they might use this instead, EOS. And padding. So it turns out that when we train an LLM, the inputs have to all be the same length, but sentences are not all the same length. So we have to do some kind of something to deal with that. So we just take the largest sentence that we would want to handle, and any sentences shorter than that, we just add these tokens to the end of it, and for padding, and so then we can make the sequence the proper length. Now he says it's when we have batch sizes that are more than one. So when we have batches that we're training, like using a whole, not just one sentence at a time, but multiple sentences, so that we can take advantage of parallelization and GPUs and so on. So the batch might contain texts of varying length. To ensure that all texts have the same length, the shorter texts are extended or padded using this token up to the length of the longest text in the batch. So actually, I'm not quite sure if this explanation is quite right, because he's implying here that it's only because of batches, and basically that if the batch is more than batch size is larger than one. But I think that it's actually has to be true regardless of the batch size, because basically without doing this, you know, this really is matrix multiplication when we feed in something into the model, and then we have to multiply it by the weights. So the dimensions have to be the same each time. So I'm not sure that it really has to do with batch size. I think it's just it has to be every sequence that we feed in has to be the same length. So I'll just put a question mark here, and this is honto, which means it's Japanese for really. So I'm not sure if it's true or not. Okay, so anyway, actually he says that GPT doesn't use any of these tokens. It only uses this one. So, and I actually thought it uses this one, but I guess maybe this is correct. And this is actually also used for padding. So apparently that's how they did this for ChatGPT, but I don't think it matters that much. Now he refers to something that we talk about later, which he says there's something called a mask, and he says that because of this this so-called mask, that in fact we don't even look at the padded tokens, but we won't worry about that now. Okay, and then he says this is also not used in GPT. And they use, as we saw earlier, byte pair encoding for their tokenizer, which breaks words into subword units, and he's going to discuss that next. So we saw this earlier, and this is the OpenAI platform, and this is the types of tokenizers that they use, and you can see the results here, and we examined this already. And this is called byte pair tokenization, or byte pair encoding. And he says this is a pretty little bit complicated scheme to learn about, and it's not necessarily worth it to investigate it in detail. And so instead, he says he's just going to use something called tick token, which implements the byte pair encoding algorithm very efficiently based on source code in Rust. And so we can use that. We can just install that and use byte pair encoding then. And we don't actually have to understand exactly how it works. And I'm not going to go into it. There are good videos on what byte pair encoding does, how it works. I guess it's a clever way to deal with unknown tokens, and generally just to tokenize. So I won't go into it, and I'll skip basically this section. But let's just see how we would use it. Use this tick token. So we install it, and can find out the version. And here we have the text, and then we use tick token get encoding GPT-2, or we could use a different one. And so that's our tokenizer. And then we can take some text here, and we can encode that text. And I guess we can say something like this to, I guess, indicate that this is going to be a special token that's allowed. And now we can, and that's now encoded as this thing, integer, so we can print that out, and we see that. So you can see that there are large numbers here because, of course, ChatGPT has a very large vocabulary to start with. So whereas our vocabulary was, I think, 1,100 and something, this vocabulary is like 50-some thousand. So we have large numbers like 34,000 and 15,000 and 50,256. Maybe this is, I'm not sure. Maybe this is end of text. Maybe that's the largest one, actually. And then they also use the same pattern for their tokenizer. They have an encode method, and they also have a decode method. And so we can try out the decode method and take these and try and decode them, and that brings them back to this, what we had at initially, I think. Yeah. Some unknown place is probably not in the vocabulary. So it's encoded. Well, actually, it's probably, let's see what it looks like if we do this. Okay, actually, I just tried to put this into the tokenizer that we saw before, and it doesn't seem to work. Now, I don't know if last time I put it in, if it worked, I might not have been paying attention. But this, it actually, when I put it in, it replaces it with something else and tokenizes something else. So I'm not quite sure why that's happening. But anyway, here, what we're supposed to do is put the text in here and then encode it, and we get that, and decode it, and we get this back again. So I'm going to skip any further explanation of the byte pair encoding. And if you're interested, I'm sure you can find explanations. Okay, so the next thing we want to do is once we have our encoder or our tokenizer, now we want to feed our data in. Now we're doing all of this for training at the moment, and so we'll have a sentence like this that we want to feed in, to our LLM, and we want to train it. And we didn't talk about this because we skipped the first chapter, but I think you're probably aware that LLMs are just predicting the next word in a sequence. So it's kind of interesting if you didn't know that. So let's say you wanted to put this, um, you had, this is your, let's say this is your prompt. The merges are determined by a frequency. So if you feed this into the LLM, basically all it's supposed to do is predict the next word. Now you wouldn't think that um, when you're using an LLM, when you type in a prompt into the LLM, you don't think it's just predicting the next word because it gives you like a whole paragraph of reply or 5 paragraphs of reply. So it doesn't seem like it's just predicting just the next word. It's giving us many words. So that doesn't sound right. But in fact, it is right. And what happens is um, it predicts. So we have our prompt. So we input that into the LLM, and then it does something. It predicts the next word. So it's going to predict like next word, NW. Okay, so that's what it predicts. And then what happens is it actually takes the prompt and concatenates it with the next word that it predicted and feeds that back into, now that you don't see this happening, but this is actually what is happening. It feeds it back into the LLM. And so we're feeding prompt and then the predicted next word in as one thing to be fed, one sequence to be fed into the LLM. And then it will predict the next word. So now we have 2 words in the answer, and then we take all of this concatenated together, feed it back into the LLM, and then it will predict the next word, and so on. So it actually is only predicting next words. Okay, so let's take that as true. So we're trying to train it, and we're trying to train it to predict next words. And we have a lot of data, a lot of training data. For example, we have the entire short story, and OpenAI has the entire internet nearly. So, so we have a bunch of data to train it on, and all we're trying to get it to do is to predict next words. So, what do we do with our training data to do that? So what we do is we have like a sentence, and we want to use it to train our LLM. So how do we do that? Well, we could just, let's say this was our sentence here. LLMs learn to predict 1 word at a time, period. But let's leave out the period for now. Okay, so we could say, okay, we want to predict the next word, so let's just take this and feed it in, and then try and let it predict this. So this is the input, and this is the output, and then we'll use that for training. Just like any other machine learning algorithm, we have the input and the output, and we use the input to predict the output. So this is our input here, and this is our output here. So and remember that we're converting these to embeddings. Each one of these is an embedding. Now we sort of lost track of that. We've only been talking about the tokenizer part and not the embedding part. We only got as far as converting them to integers, but we sort of forgot about the fact that then our next step will be to take these integers and typically turn them into into a vector, because each one represents a word, or we could say a token, and we said back in the beginning that we have words and we want to represent them as vectors in a so-called vector space. So we have to do that with each one of these. we have to represent it as a vector. Now we didn't, and we said that we could sort of take some pre-coded set of associations between these words and vectors, or we could sort of create our own on the fly. But we just skipped. We haven't gone back to that at all. We only got as far, really, so far in terms of the coding, at least, of getting the integers. But we do have to think about the fact that we're feeding in, when we're doing this, that we're actually feeding in vectors to the LLM, or embedding. So, okay, so each one of these is an embedding, or a vector. But let's forget about that for a moment. Anyway, we want to take this as the input and predict this as an output. Okay, great. So we have now we have a training example that we can use to do some training. But I guess these guys said, let's not be wasteful, and maybe we can get a whole lot of training examples just from one sentence. So, we might have thought at first glance, well, we'll just take all of these to predict this. But probably later on we might say, we're kind of wasting this this sentence in a sense, because we can get more training data out of this. So what do we mean? So we could take just the first word and try and predict the second word. And so we have a training example. This generates this. So that's one training example from the original sentence. And then we can get a different training example. The first two words predict this, or generate this. So we get a second training example out of this single sentence. And then we get a third training example out of the single sentence. And we get a fourth one and a fifth one, and so on. So that's kind of like a conservation of training examples. Like, don't waste your training examples. Okay? So that's the idea here. So they didn't want to waste, so they did this. And it also probably, I'm not sure of the reasoning, but it probably makes sense for other reasons, like it kind of broadens the outlook of the LLM or something. I'm not quite sure how they would state that. But anyway, that's what we're doing. Now, here he brings in the idea of mask. So let's think about this. Let's get some idea of what this word mask means here. So during training, we mask out all the words that are past the target. So, this is all in gray here. So this is kind of masked out because we don't need it, and we don't want it. We don't want to feed it to the LLM either, or we don't want the LLM to look at it either, because that would be a completely different. It would be training in a completely different way. It would be taking LLMs and this 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 to predict learn. And that's probably a lot easier than just using LLMs to predict learn. But that's not our task, because when we're using the LLM, we don't have the end of what we want the reply to be. That's not what we do. That's not what we want. That's not what we are giving, right? That's not how we're using the LLM. We want to give it a prompt and have it predict everything afterwards. We don't want to have to say what part of the end is going to look like. So this doesn't make sense to feed in these grayed out words. So we do need to mask these. Now, because masked in the sense that we are giving it the whole sentence, but it's only looking at the beginning. So they say we mask out all the words that are past the target. So in this one, the target is learn. In this one, the target is to, and so on. Note that the text shown in this figure must undergo tokenization before the LLM can process it. However, this figure omits tokenization. It's the tokenization step for clarity.